Okay, let's get started. So we've sort of finished up talking about different subgroup tests last time. So now we're going to sort of start talking about different types of groups into a lot of detail. So today we will talk about something called cyclic groups, and we'll prove a couple of results about them. And then on Friday, we will prove something called the fundamental theorem of cyclic groups and look at some consequences of that. So let me go ahead and tell you what a cyclic group is. So let's just establish some notation first. So I'm going to let G be a group. And I'm going to let A be an element of G. Then we'll have this notation. So if I write two brackets surrounding an element A of the group, then that will denote the set of all A to the n such that n is an integer. Okay, and this is called the subgroup generated by the element A. Okay, so I guess one thing is that we need to show that this is in fact a subgroup. So how can we see that it's a subgroup? Does anyone see why maybe using a subgroup test that this would be a subgroup? Yeah.
Well, it's closed under the optimization. I'm sure because all of the layouts should be in G. It also has A0, so it has the identity, right?
Yeah. Yeah, so it's closed, it has the identity, and
The operation itself is associated by definition.
yeah, and then what else do we need to check? Yeah, inverses. So yeah, inverses are in here because we have like also the negative exponents potentially, so inverses are also good. Okay, so this is a subgroup generated by the element A. Okay, so if we actually have that our group G is equal to the subgroup generated by A, then we say that the group G is cyclic, and the element A is called a generator. And one like observation that I'll make is that every cyclic group is abelian. And this is just because if your group is cyclic, then every element is written as some power of A, and so you can just like by reassociating kind of re-express any product as like as interchanging those two products. Okay, so every cyclic group is abelian, and I'm going to give you a few minutes to think of some examples and non-examples. And then we'll make a list of like sort of groups we know and whether or not they are cyclic or not. So go ahead and take a few minutes to think about and discuss like some groups that are examples and non-examples. need water? Okay, so what did we come up with for examples and non-examples of cyclic groups? Yeah.
Like if you just take any like value in a real number and you can just like pick a set of all the powers of that.
Yeah. Okay, so if we could take like inside of the real numbers, so I guess inside of R star. So we take out 0, and with multiplication, inside of that we have a subgroup where we just take any element and look at the powers of that element. Other examples or non-examples? Did anyone come up with a group that isn't cyclic? Yeah. Yeah, so the permutation group S3 is not cyclic, so you can't like write every element of S3 as just like a power of one single element. Good. Other examples? Yeah. Yeah, so the integers, and what's a generator for the integers? I guess with addition. Yeah, so this is generated by just the element 1. You could take the element -1 as a generator also. Good. Other examples? Yeah.
Like some of the U, like relatively fine are cyclic, sometimes not. The U of 10 is cyclic, but U of 8 isn't.
Yeah, so some of the U groups are cyclic and some of them are not. So I didn't verify this. U10, I guess you showed that it is cyclic. What is it generated by? 3. And then U8, yeah, I had also written down as an example of something that wasn't cyclic. What about groups like using addition modulo a number? So like Z6, where does this fall? Cyclic or not cyclic? Yeah. Yeah, so this would be cyclic. We'll prove later that these like groups of this form are actually all cyclic, and you can generate them with any number that's relatively prime to the thing that you're what's the verb for modulo? Modulating? You can, yeah, so this is like generated by, for example, 1 or 5 is another generator. Okay, so those are some examples and non-examples. So let's prove a theorem. I'm just going to make a new page. So this is going to be the first of several results that sort of like build up to the fundamental theorem of cyclic groups. And it has a couple of parts. So we'll let G be a group. And A be an element of G. Okay, then this is just going to break into two parts, and one is if A has infinite order, and the other one is if A has finite order. So if A has infinite order, then all powers of A are distinct group elements. Okay, so let's just recall that the order of A is the least number n with A to the n equal to the identity, and if such an n does not exist, then it's said to have infinite order. Okay, and then the second part says that if A has order n, then the group generated by A. By the way, if you're interested in LaTeX, you get these things by doing L angle and R angle. So that gives you the left and the right of those symbols. Okay, anyway, so this is equal to the set E, comma, A squared, and so on up to A to the n minus 1. Okay, so every power of A will be equal to one of those. And as a second part of the statement, AI is equal to AJ if and only if n divides I minus j. Okay, so let's prove this theorem. So I'll start with the first part and just fill in the proof here. So if A has infinite order, then there is no n with A to the n equal to the identity. Okay, so let's suppose that we do have some power of A to the I, that is equal to some other power, A to the j. Then we will prove that in fact I is equal to J, and that will show that all of the elements of the subgroup generated by A are actually distinct group elements. So if A to the I is equal to A to the J, then AI minus J is equal to E. But there's no, sorry, and this should say that this is the least positive N. So that means that A to the I minus J is equal to E. And I guess A to the J minus I is equal to E. So that means that these two numbers, I minus J and J minus I, are, neither of them is positive, so we must have that I minus J is equal to 0. So I is equal to J. So we've shown that if I have some power of A and it's equal to another power of A, then necessarily that the exponents on those two powers were also equal. So that shows that all powers of the subgroup generated by A are distinct group elements. Are there questions about this part of the proof? Okay, so let's move on to this second part. And I'm going to break this into two parts as well. So I'll just do this first bit, and then I'll come to like 2B after. Okay, so what we want to show is that the subgroup generated by A is equal to this set. So first of all, let's just observe that the elements listed here are distinct. And if not, this would contradict the fact that n is the least positive number with a to the n equal to the identity. So otherwise, this contradicts that n is the order of A. Okay, so certainly we have, just move this further down. So certainly we have that this containment, right? That the subgroup generated by A contains all of these things. Okay, so this is true. So now let's suppose we'll prove the other containment. So suppose A to the K is some element of the subgroup generated by A. Then I'm going to move this even further. Okay, then by the division algorithm, we can write K is equal to some multiple times n plus r, where 0 is less than or equal to r is less than n. Okay, so then a to the k, what is this equal to? This is a to the q times n times a to the r. And This is going to be a to the n to the q, so this is just the identity. But we know that r is a number between 0 and n minus 1, so this shows that this is actually an element of this set. So we're done with this part of the proof. Put a box. Are there questions about this part? Yeah.
Can you say again why a to the q n is equal to e?
Yeah, so this, okay, so what is this? This is a to the n to the q, but n is the order of a, so this is e to the q, which is then again e. Yeah. Other questions? Yeah.
For the first part, how do we know that the elements are distinct based on the order?
Okay, yeah, so let's see why these are distinct. So suppose like a to the j is equal to a to the I for something in here, then whichever of those is bigger, we'll just leave that one. So say j is bigger, we would have a to the j minus I is equal to e, but this contradicts. So this would be a number that's smaller than n, so that can't happen. Yeah. Other questions? Okay, let's move on to the last part of this. So again, we're assuming that A has order n, and then we're going to prove that a to the I is equal to a to the j if and only if n divides I minus j. Okay, so n is the order of a still. Okay. So let's assume that a to the I is equal to a to the j. Then that means that a to the I minus j is equal to the identity. Okay, so that means that, so let's use the division algorithm on I minus j and divide it by n. So by the division algorithm, we have that we can rewrite I minus j as sum q times n plus r, where 0 is less than or equal to r is less than n. So we have that a to the I minus j is equal to a to the qn times a to the r, which again, this a to the qn will be identity, so this leaves us just with a to the r. And we also previously had observed that a to the I minus j was equal to the identity. So altogether we have that a to the r is equal to the identity. But we also know that n is the least positive integer that has this property, so that forces r to be equal to 0. Because otherwise that contradicts the fact that n is the order of a. Okay, so then what does that mean? It means that I minus j is equal to q times n, so n divides I minus j. Okay, so that was one direction, so that was the forwards direction. And so we should also prove the reverse direction. So if n divides I minus j, Then a to the I minus j is equal to a to the n times something. We can just call this m, I guess. And that's equal to the identity. So we have that a to the I is equal to a to the j. Okay, are there questions about this part of the proof? Yeah. Yes, so, okay, so the R is the remainder from the division algorithm. So it is some number between 0, and it could be equal to 0, but it's strictly less than n. And we showed that a to the R is equal to the identity. And we also know that n is the least positive integer that has that property. So what are our options for R? Well, they could be positive integers, which we've sort of excluded because n is the only thing that's allowed to do that. Or it could be 0, so it's like forced to be 0. Does that make sense? Okay. Other questions? But n is the least positive integer that has this. No, because 0 isn't positive. Yeah. Okay. Okay, so here's a couple of immediate consequences from this. So here we get some corollaries. So corollary is just kind of like a fancy word for like these statements follow immediately from the theorem. So the first one is that for any element A of a group, we have that the order of A, which is the thing, so that's the least positive n such that a to the n is equal to e. The order of A is equal to the order of the subgroup generated by A. Okay, so these notations are consistent. And why do we see that from the theorem? Well, we proved that the subgroup generated by A consisted of exactly these elements and that they were distinct, so there are n of them, right? So that shows that these two things are equal. Then a second corollary is that if G is a group and A is an element of G of order, I guess this is ambiguous because it could be talking about the group or the element. A is an element of G and the order of A is equal to n. Then if A to the K is equal to E, then n divides K. Okay, so if you take some power of A and you get to the identity, then that means that n definitely divides that power. And that just comes from applying this second part of the theorem with one of I or j equal to 0. I guess we could take j equal to 0. And we get n divides I. Okay, so those are special cases of this theorem that can come up and that are useful. Okay, so let's just take a step back and sort of look at what is like the big picture of this theorem. So if the order of A is finite, then what is the group operation in this, in the subgroup generated by A? So basically, multiplication, so let me erase this. So then multiplication inside of this group, the group generated by A, is done by addition mod n as follows. So we know that if I plus j mod n is equal to k, then that by this theorem that tells me that a to the I times a to the j is equal to a to the k. Okay, because like any if I take this product, then in the exponent I would get I plus j, but any existing copies of n in there will just send a to that power, which is a multiple of n, that will go to the identity, and so you're just left with the remainder on division by n. And that's exactly given to you by taking this addition mod n. Okay, so these, so basically this is just saying that groups of this form like behave in a very predictable way, and we're going to be able to leverage that to say a lot about their structure. And so that's like moving towards this fundamental theorem of cyclic groups. Okay, let's prove another theorem. So let's let A be an element of order n in a group G, and let's let k be a positive integer. Then we can say what the group generated by a to the k is. And this is just equal to the group generated by a to the GCD of n and k. So what this is doing is we're moving, so I just said that, so the fundamental theorem of cyclic groups is going to say something about the structure of cyclic groups, and in particular, it's going to tell us like what are all of the subgroups. So this is like moving in the direction of figuring out what all of the subgroups are. Okay, so we have this, and another piece of this, which is like the piece that gets used, I think, the more frequently, is that the order of this group is equal to n divided by the GCD of n and k. Okay, so this part is important. This comes up a lot. Okay, are there questions about the statement of the proof? Yeah. Okay, yeah, so by this, we have this corollary, which says that they're like, those are the same thing, yeah. Other questions? Yeah.
Here we are using a to the k as the generator, right?
Yeah.
Instead of a.
Yeah. Okay, so let's go ahead and prove this. Okay, so let's just start off by setting, just to save us a little bit of writing, we'll set D to be this GCD of n and k. And you can remember that, I guess, by like D standing for divisor. So it's like it's that greatest common divisor. And then let's let K be, so K is our, the number that we're raising A to. And we want this to be equal to D times R. So R is like whatever is left over after dividing K by D. Okay, so let's start with the first part, and we'll do this by proving both of the containments. So let's start off with A to the K is a subset of A to the D. Okay, can we see why this is true? So let's take an arbitrary element of A to the K. So that'll look like some multiple of K. Okay, so then why is this contained in the subgroup generated by A to the D? Yeah.
Because you can like arrive at it using D just by multiplying it, like to get K and then that times M.
Yeah, so we can rewrite A to the M, A to the MK. So let's just sub in for how we had written K. So this is A to the MDR. And this is a power of D, right? So this is contained in A to the D. So for this part, we're good. Okay, are there questions? The other containment is harder, so let's do that one. So now we'll show that A to the D is contained in A to the K. So the way that I'm going to do this is to just show that A to the D is in A to the K, and then that implies that automatically any other power will also be in A to the K. So this implies since this subgroup generated by A to the K is a group. So we have closure. Okay, so let's do the following. So we're going to use the GCD as a linear combination theorem. So there exist S and T, and I know this is getting to be a lot of variables, so we'll try to keep these straight as much as possible. So D is our GCD, and we're going to rewrite that as a linear combination of N and K. So there exists S and T with D written as a linear combination, Sn plus KT. Okay, so let's raise A to that power. So A to the D is equal to A to the NS times A to the KT. Okay, but then A to the NS, let's recall N is our order. So A to the N is identity. So this gives us E times A to the KT. Which is, let's just rewrite this as A to the K to the power T. And this is a power of A to the K, so that means that it is an element of the group generated by A to the K. Okay, so that completes this part of the proof. So this is GCD is linear combination. Okay, are there questions up to this point? So we have proven this part, right? So now we have to show that the order of a to the k is n over GCD. Yeah.
Can you explain again why a to the ns equals c?
Yeah, so this we can think of as a to the n to the s, but n was the order of a, so that means that raising a to the n power gives me identity. And then that just gives me identity again. Yeah, there's like a lot of number, like symbols involved, so it's hard to keep track of like which letters were which thing. But yeah, n was the order. Yeah, other questions? Yeah.
Can you explain again why a to the MDR is a to the for the first?
Yeah. So up here, so this is a to the d to the mr. I wrote mn. mr. And that's a power of a to the d. Yeah. Any other questions? Bean is dead. Bean. Okay, so let's do this this second part. So we want to show that I'll just rewrite down here. So we want a to the k, the order of this thing. We want to show that this is n over d, where d is the GCD of n and k, and n is the order of a. Okay, so let's let d prime be any divisor of n. Then we have that e is equal to a to the n, and this is equal to a to the d prime times n over d prime. So this means that the order of a to the d prime is less than or equal to n over d prime. Okay, but if the order of a to the d prime is smaller than n over d prime, then there is a smaller power let me say it this way. So then there is an n prime less than n with a to the n prime, a to the n prime equal to the identity, which contradicts that n is the order of a. Okay, so we can conclude that the order of a to the d prime is in fact equal to n over d prime for any divisor d prime of n. Okay, so then if we're looking at a to the k, so this is, of course, equal to the order of the group generated by a to the k. And this is equal to, why is this equal? All right, I'm not following what my notes say, but let's figure this out. So we just showed that the order of a to the d prime is equal to n over d prime. So this should be equal to what? All right, I'm gonna write what's in my notes and then we can figure out why this is true. So I wrote that this is equal to a to the order of a to the d. But I don't see why that's true. Does anyone see?
That's from the last thing we proved, where we proved that the two sets were the same. We proved the thing.
Oh yeah. Okay. Okay, good. So, okay, right. So of course, so we had this corollary. Thank you. So this is, and by the first part of this theorem, this is equal to the group generated by, so this is the first part of our theorem, this is equal to the group generated by a to the GCD. Okay, so this is a to the d was our GCD. And this is equal to the order of a to the d. And by this first step, this is equal to n over d, which is the GCD. So that proves this second part. Are there questions about this part of the proof? Yeah.
Why is it the case that the order of a to the d prime is less than or equal n over d prime?
Okay, yeah, so let's go back to this line. So we showed that raising this element, a to the d prime, to this power gets us to the identity. So that shows that whatever the order of this thing is, it has to be less than or equal to this. Like this gives you an upper bound for what the order is. Yeah, other questions? Okay, so next time I'm gonna start with an example to illustrate like why we have this, like why did we even bother with this theorem? Why do we do this? Why does this make our lives easier? And then we will prove the fundamental theorem of cyclic groups, and then we'll look at some consequences for various types of groups. Do you have a question? we have A, the N, Okay, so let's suppose we can replace this with a smaller number. So let's say K. That's the N over D prime with A to K. Well then also A so we're supposing K is the order of oh wait, okay, so this is the order of D prime. Okay, so then A to the D prime times A. So this is then the identity. And then D prime over K is less than N and takes A to the identity. So that means that N is not the order of A.
Oh, okay.
Yeah.
Thank you. Hey, I had a similar question about this one. You said this gives like an upper bound, but then by definition, if this whole thing is equal to E, then isn't N over D prime? Isn't this the order? Why is
Okay,
it?
so the order is like the least number that does that. So we just found a number that does it, but there could be like a smaller one.
But then, why does this give a like upper bound on what?
Yeah, okay, so if we had like a number larger than this that also had this property, we already know that that one's not the order because we have a smaller one that does it.
Oh, because by definition, the order has to be the smallest.
Yeah.
And so the rest of the proof was like, what if this were smaller than?
Yeah, so what if there is an order that's smaller? So let's say K. Hopefully K isn't a number I used elsewhere in the proof, but like let's say K is a smaller number that also achieves this.
Okay.
Well, then this is a number that's smaller than N.
Oh.
That would